I posted a video for you from Patrick JMT that showed how to find eigenvalues and eigenvectors for a 2x2 matrix, and I thought I would give you a video where we practice this just a little bit. So just a reminder of what eigenvalues and eigenvectors are, we need to know more about them. So almost all vectors change directions when they're multiplied by a matrix. We use matrices to transform vectors, and we can use them to transform a number of things in math. If we multiply a vector x by a transformation matrix A, the only vectors that do not change direction are those that are pointed in the same direction as AX. We call these special vectors eigenvectors. If we multiplied an eigenvector of A by A, the vector AX is a number lambda times the original x. Thus we say that AX equals lambda x. And the number lambda is associated with A. Lambda is what we call the eigenvalue of the n by n matrix A if and only if the equation A minus lambda I all times x equals 0, and it has a non-trivial solution. So remember, I is the identity matrix, so we're taking matrix A and we are subtracting lambda from the diagonals, right? Because we're taking A here, which is n by n, and we're subtracting lambda times the identity matrix. So let's say we have a 2 by 2 here. We're doing a 2 by 2 identity matrix will be 1, 0, 0, 1. And when we do that, we end up with A, 1, 1 minus lambda, A, 1, 2 minus 0. And then we get A, 2, 1, and then A, 2, 2 minus lambda. Since A minus lambda I is a linear combination, we are really seeking to find out where the determinant of A minus lambda I is 0. And this should remind you quite forcibly of using the Wronskian to determine linear dependence. Let's try a couple of example problems. Let's look at example problem 1. We want to find the eigenvalues and the corresponding eigenvectors for a 2 by 2 matrix A with elements 2, 3, 3, negative 6. So here our A minus lambda I is going to yield 2 minus lambda, 3, and 3, negative 6 minus lambda. And we want to find the determinant of this matrix. So we want to find the determinant of A minus lambda I. And that would be the determinant of 2 minus lambda, 3, 3, negative 6 minus lambda. And remember, our determinant is the upper left, 2 minus lambda times the lower right, negative 6 minus lambda, minus the upper right times the lower left, 3 times 3. So in this case, and we want to set it equal to 0 and solve for lambda. So in this case, 6 times 2, well 2 times negative 6 that is negative 12, plus a 6 lambda, minus a 2 lambda, plus a lambda squared, and minus 9 is going to equal 0. So we have lambda squared plus 4 lambda minus 21. Multiplies to give me 21, subtracts to give me 4 would be 7 and 3. So we'd have lambda plus 7 times lambda minus 3 equals 0. So lambda 1 equals negative 7, and lambda 2 equals positive 3. So we already have part of the solution we were looking for. We found the eigenvectors, or sorry, the eigenvalues. Now let's find the corresponding eigenvectors. Let's start with lambda 1 equals negative 7. When we plug it in to A minus lambda I, we get 2 minus a negative 7, 3, and then 3 and negative 6 minus a negative 7 times x1, x2 equals 0. Or we get 9, 3, 3, 1. And we can make it an augmented matrix by drawing a line and putting the zeros in. And we can transform this by saying, okay, I can take negative 1/3 row 1 and add it to row 2 to get my new row 2. And I can take 1/3 of row 1 is going to be my new row 1. And I end up with 3, 1, 0, 0, 0, 0. When we're finding eigenfunctions, or sorry, eigenvectors here, we always want to make sure that we get one row of zeros here. If that doesn't happen, then I would check that you didn't forget to subtract the lambda from one of the diagonal entries in your matrix, because you should always end up with one row of zeros. So in this case then, this would translate to 3x1 plus x2 equals 0. Or x2 equals negative 3x1. If I let x1 equal 1, or yeah, I could let x1 equal 1 here, then x2 would be negative 3 times 1, which would be negative 3. So our first eigenvector here is going to equal 1, negative 3. So we've got one eigenvector done. Now we need to do the same thing for our other eigenvector, which is 3. So I'm going to scroll up a bit and see if I can get some more space down here. So let's do our other eigenvector. Lambda 2 equals 3. When we plug that in, 2 minus 3, 3, 3, negative 6 minus 3, times x1, x2, and it equals 0, 0. A minus lambda I, right? We need it to help us solve ax equals 0. So we end up with 2 minus 3 is negative 1, 3, 3, and negative 6 minus 3 gets us negative 9. And we can make it an augmented matrix and throw the zeros on here. We could do a negative 1 times row 1 is our new row 1. And we could say 3 row 1 plus row 2 is our new row 2. And when we do that, we find out that we get 1, negative 3, 0, 0, 0, 0. Or in this case, then we know that x1 minus 3x2 equals 0. So x1 equals 3x2. So if I let x2 equal 1, then x1 would equal 3 times 1, which is 3. So our second eigenvector is going to be the column vector 3, 1. And we've found everything that our problem asked us to find. We found both of our eigenvalues, both negative 7 and 3, and we found their corresponding eigenvectors, 1, negative 3, and 3, 1. Let's try another one. So now we've got our 2 by 2 matrix A is 1, 2, 2, 4. So A minus lambda I, the determinant of that is going to give us the determinant of 1 minus lambda, 2, 2, and 4 minus lambda, which will yield 1 minus lambda times 4 minus lambda minus 2 times 2, and we want to set this equal to 0. So we end up with 4 minus 4 lambda minus 1 lambda plus lambda squared and minus 4 equals 0. So our 4's cancel out, and we're left with lambda squared minus 5 lambda equals 0, or lambda times lambda minus 5 equals 0. So lambda 1 equals 0, and lambda 2 equals 5. So we've already found one part of what the question was asking. So now that we know our eigenvalues, let's find our eigenvectors. So let's start with lambda 1 equaling 0. If we plug that in, we get 1 minus 0, 2, 2, 4 minus 0, times x1, x2, equaling 0, 0, which would give us the augmented matrix 1, 2, 0, 2, 4, 0. And this is actually an easier reducing than we did, or reduction I should say, than we did on the last one, because we don't need to do anything to row 1. All we're going to do is say negative 2 row 1 plus row 2 is going to equal our new row 2, and we end up with 1, 2, 0, 0, 0, 0. So we have x1 plus 2x2 equals 0, or x1 equals negative 2x2. If we let x2 equal 1, then x1 will be negative 2 times 1, or negative 2. So our first eigenvalue here, or eigenvector here, is going to be negative 2, 1. It wouldn't be wrong to let x2 equal negative 1, and then x1 would be positive 2. It would be the same thing. That is also an acceptable eigenvector. Let's see what we get when we look at our eigenvalue, our second one, that's 5. Well, we would get 1 minus 5, 2, 2, 4 minus 5, times x1, x2, equaling 0, 0. Or we get the augmented matrix negative 4, 2, 2, negative 1, and zeros. We do have to do a little extra work this time, because we're going to have to say negative 1/2 row 1 equals our new row 1. And we're going to say row 1 plus 2 row 2 is our new row 2. And when we do that, we find out that we have 2, 1, 0, 0, 0, 0. Right? That's what we end up with. 2, 1, 0. Oh, whoops, sorry, 2, missed a sign, negative 1. 0, 0, 0, 0. So in this case, we end up with 2x1 minus x2 equals 0, or 2x1 equals x2. So if we let x1 equal 1, then x2 is going to equal 2 times 1, which is 2. So our second eigenvector is going to be 1, 2. And that's the rest of what we were asked for here. I didn't give you any homework problems for this section because we're going to be doing a lot of eigenvalue and eigenvector finding in the rest of chapter 10. So make sure you have practiced with these.